going to finish up 6-1. So we started talking about angles, and the last thing we did in 6-1, part 1, was converting between radians and degrees. Well, we're going to talk about a formula in this section for arc length, and this is a formula that uses radians. So if they give you something that you need to plug into this formula and it's not radians, you need to fix it, okay, and convert to radians. All right, so let's talk about arc length. Okay, let me draw a couple pictures. Let's take this. Actually, you know what? Let me do it like this. Okay, so I'm going to draw an XY axis, and then I'm going to draw a circle at the center. And let's make another one of those. What I'm going to draw in this one is a 90-degree angle, and then I'm going to double it, and I'm going to draw that in the other one. If we double 90, we get an angle that's how big? 180. So here's what a 90 would look like. In standard position, initial side would point to the right, terminal side would go straight up. This would be the arc on that circle created by a 90-degree angle. Any question on that first picture? So the second picture, I'm going to draw a 180. So my initial side would point like this. How would my terminal side point if it was 180 degrees? Yeah, Luke?
I wasn't reading the house.
Do you know? Yeah. So it would point. Can you give me a specific way it would point?
On the x-axis, going to the left.
Yeah, going to the left. So it would be on the negative part of the x-axis. Okay. So there's a 180-degree angle, and the arc would look something like that. So when I doubled the size of the angle, the question is, what happened to the size of the arc? Yeah, it doubled. Okay, so there's a direct relationship between the size of the angle that you draw right here and the size of the arc that you get. If you double the size of the angle, you'll double the size of the arc. If you made the angle half as big, what do you think would happen to the arc? Yep.
They do the same thing.
Yeah, we'd always do the same thing. So there's a name when one thing changes and the other thing changes exactly the same way. Does anybody remember what that's called? Like if one thing doubles, the other thing doubles. There's a name for that. Yep.
Is it a mirror?
No, not a mirror. Yep.
Proportional?
Proportional, yeah, it's proportional. So arc size and angle size are directly proportional. Because they are proportional, that means when I set up my formula to figure it out, I can set up a proportion. Okay? You can only use a proportion if two things are proportional, and arc size and angle size are. Okay, so I'm going to draw another diagram. And inside that diagram, I've drawn two arcs and two angles. I've labeled each angle with Greek letters. And what's the name of the Greek letter?
Theta. Theta.
Theta. So I've drawn angle theta, and that corresponds to arc S. And then angle theta 1 corresponds to arc S1. So now I want to set up a proportion, and I want to use these four things. So remember, the idea here is that, like, if this was, just make up a number. Let's say that this was 100 degrees. If this angle was 100 degrees, let's say that this arc was 2 centimeters. If you double this angle and make it 200 degrees, then the arc would be how much? Yep. It would be 4 centimeters. It would double. So as long as you know the size of one angle and the size of the arc connected to it, you can figure out any other arcs and angles in the circle. You just have to know one pair, right? So let's see if we can set up our proportion. Anybody have a guess what I could put on the left-hand side using 2 out of 4 of the things that are circled in blue? Yep.
Theta over S.
All right, so we could do theta over s. There's lots of ways we can set up that side. But now that we set up the left side as angle over arc, the right side has to be the same way. So what could we fill in on the right side? Yep.
Theta 1 over S1.
Right, theta 1 over s1. Now the problem with that proportion is right now there's no numbers in it. It's pretty useless. It's kind of like if I wanted to convert between feet and inches, and all I did was write this down. Feet, inches, feet, inches. Well, yeah, you set it up the same way on each side. Feet over inches, but you don't have any numbers in there. Okay, you've got to fill in a fact that's true on one side. So we could use something like 12 inches equals 1 foot. Now that you have a true statement on one side, you can plug in anything on the other side and figure it out. Let's say you wanted to know how many inches in 15 feet. As long as you know this, then you can figure out that by cross multiplying. But that's the whole key. You have to know that. Okay, so how do you get that? Well, we've got to fill in a fact that's true, right? And we're going to fill it in right here. First thing I talked about when we did degrees and radians yesterday was a special connection between the size of the arc and the size of the radius. There's a connection between the two as long as this angle was a certain size. Anybody remember from yesterday? If this angle is a certain size, then there's a connection between the arc in red and the radius in black. I need to know what size angle I have to use. And then I want to know the connection if I use that size angle. Yep.
Is it, if the angle is 90 degrees, is the arc in the initial line the same?
I don't think we said the angle was 90. Did say the angle was something, but not 90. It was the very first thing we talked about. Yep.
Repeat the question.
So we mentioned something yesterday that if this angle is a certain size, then we automatically know a connection between the arc in red and the radius in black. I want to know what size angle I'm talking about, and then I want to know the connection between the radius and the arc.
Is it 1 radian?
Okay, if this angle is 1 radian, then what happens? Yep.
Radius is equal to
The radius is equal to the arc, yes. If this angle is 1 radian, then the radius is equal to the arc. That's just like saying if you have 12 inches, that is equal to 1 foot. Why? Well, that's the definition. 12 inches equals 1 foot. So same idea here. If that angle is 1 radian, that automatically means that this arc, S1, would come out the same size as the radius. So that's the true fact that we're going to fill in on the right-hand side. If theta 1 equals 1 radian, then S1 is automatically equal to the radius. Once we fill that in on the right-hand side, then we've got something kind of like this. We'll have a true statement on the right, and then we'll have something on the left we can solve for with a variable. Okay, so let's fill it in. So the left side, we don't touch that. Okay, that's information that they would have to tell us in the problem. But the right side is going to be our true statement. If theta 1 is 1 radian, that automatically means the arc equals the radius. That's like writing in 1 foot there's 12 inches. It's just a true statement. And now we can use that true statement to figure out things that we don't know. Okay. How do you solve a proportion? Yeah.
You cross multiply.
Yeah, you cross multiply. So what would you multiply here if you do what you just said?
The theta by r.
All right, so we're going to do those two.
And the s by 1.
Wait, what's s times 1?
I don't know how much the s is.
S is just s, just a variable.
Wouldn't it just be S?
Yeah, s times 1 is just s.
Anything.
And then r times theta is r theta. So that is the formula for finding the length of an arc in a circle. The arc length equals the radius times the angle. Now, there's something we assumed about the angle early on in the problem. What units did we assume we were working in? Radians. Just like when you write a proportion like this, you're assuming you're working with feet and inches. If you're working with miles, well, that's not going to work. It's not the right units. So we used the fact that we learned yesterday, and that fact was in radians. Because we based everything off that fact, all angles in this problem have to be in radians. They cannot be in degrees. Okay, so the idea is they'll give you 2 out of 3 of the letters, and then you'll solve for the one that you don't know. So S is the arc length, R is the radius length, and theta is the angle measured in radians. Okay. Does everybody have the arc length formula? All right, so the first one, I'm going to draw a picture of it, and I'm going to write it in words. In general, you're not going to see both in a problem, but for the first one, I did both. So the goal here is you're finding the length of this arc in red. And they tell you that you have an angle inside a circle that's pi over 4 radians, and the radius of the circle is 2 inches. So what's the first thing that we're going to need to try to figure this out? Yes, yep.
Do we have to set up a proportion?
We don't have to set up a proportion, but we need something to plug into. Yep.
The arc formula?
We need the arc length formula, yeah. What's the formula for the arc length?
S equals R times theta.
S equals r times theta, and then we'll just start filling in what we're given. Okay, what are we going to fill in for S?
X? We don't know.
We don't know. That's the whole question. Find the length of the arc. So S is just going to stay S. If that's the variable, then that means nothing else can be a variable. We have to have numbers for the rest of the problem. What are we going to fill in for the radius?
2.
2 times. And what are we going to fill in for the angle? Yep, pi over 4. And to use the arc length formula, what unit is the angle supposed to be in? Yep, radians. And what angle, what unit did they give us on the angle in this problem? Radians. So we don't have to convert anything. They gave us pi over 4 radians. That's exactly what we need. So if you want to think of the radius as a fraction, you can make it 2 over 1. And what do you get when you multiply straight across and reduce? Yeah.
Pi over 2.
Yeah, we get pi over 2. Now we do need a label on that. What did we just find? We found the arc length. Okay, so we found a length. So what should we put for a unit on that?
Inches.
Yep, in this problem, it's inches. Okay, you have to look at whatever units they used for length. But this problem was inches. And that's it. We don't round that unless they specifically say to. So I'm just going to leave it as pi over 2 inches. If you did round it, it's about 1.57 inches.
You wouldn't need to have the same denominator?
No, not when you're multiplying.
Okay.
No, common denominator is only for adding and subtracting. Multiplying, you just go straight across. If you made the denominator the same, well, it would just come out exactly the same. So if you made it 8 over 4 times pi over 4, now you have, let's see, multiply top and bottom by, yeah, when you multiply straight across, you get 8 pi over 16. But then 8 pi over 16 just reduces to pi over 2. So there's no need to find a common denominator then when you're multiplying. All right, let's try this one. It says find the radius of a circle if the arc length is 3 pi feet and the central angle is 60 degrees. So Nick, what's the first thing that I'm going to need to write down that's going to help me do this entire problem?
Formula.
Yeah, I need the formula. Okay, what's the formula for arc length?
S equals R times theta.
Yep, S equals R times theta. And let's start filling in left to right, whatever they give us. Do we know S?
Yeah.
Yeah, what's S?
3
3 pi. Yeah, they tell us the arc length is 3 pi. Okay, do we know R? No, that's the whole question. Find the radius. Do we know theta?
Yes.
Okay, what's theta in this problem?
60 degrees.
60 degrees, but there's a problem with that. What's wrong with it? Yep. It's not in radians. So if you fill in 60, it's going to come out wrong. Okay, we need off to the side, let's convert 60 degrees into radians. What do we multiply by to change degrees to radians? Yep.
Pi.
And multiply by pi, yep,
Over 180.
over 180. So pi over 180. Degrees will cancel. And 60 goes into 180 3 times. So what you should be filling in for your angle is pi over 3 radians. All right. Now we want to get r by itself. How can I get rid of this times pi over 3? Yeah?
Well, you divide pi over 3 on both sides, but you really have to do the reciprocal.
Yeah, you could divide by pi over 3, but it's easier just to multiply each side by the reciprocal, which is 3 over pi. When you multiply by the reciprocal, lots of things are going to cancel. The 3's, the pi's, and the pi's. So what do we get for a radius in this problem? Yep. Can you be more specific? I need a little more information than 9.
Is it 9 radians?
Did we just solve for an angle?
Yeah. You should say it.
What did we solve for?
Degree.
If we solved for an angle, then yeah, we should put radians, but
We solve for the radius.
we solved for the radius. We didn't solve for an angle. So you don't measure the length of a radius as an amount of rotation.
Oh, so 9 feet.
It should be feet. Right? That's a length, that's a length, that's an amount of rotation. So because we solved for the radius, that's a length measurement. And in this problem, they use feet. 9 feet. Okay, so 6A and 6B were each a little different. 6A, you found the arc. 6B, you found the radius. The only one I didn't do was finding the angle, but it works the same way. Okay, any questions on that one? All right, so next thing we're going to look at is what's called angular velocity. So we already have an idea of velocity is speed, right? It measures how fast something's going. And there's already a concept of speed we use a lot to measure the speed of something moving in a straight line. This doesn't measure the speed of something moving in a straight line. Does anybody have a guess what angular velocity measures? Yeah, Julia?
And something moving at an angle,
Something moving at an angle?
right?
Okay, yeah, something moving at an angle. Could someone explain that maybe in a easier to understand way? What would that mean, something moving at an angle?
Something.
How would an object be moving if it was moving at an angle? Yeah,
Is it rotating?
rotating, yeah. So we're measuring the speed of something rotating. Which-
That was a complete guess.
I think it's easier to understand that idea because we think of rotations per minute, like RPMs. That's an example of angular velocity, how fast something is rotating. So when we do angular velocity, if they do not specify a unit, I always want you to do radians per whatever, radians per time unit. Could be radians per minute, radians per second, radians per day, but we always want to use radians, unless they say not to. There's only 3 units that we've used to talk about an amount of rotation. One is radians. What's the other one? So what units can be used to describe rotation? Radians, yep. Degrees, and one more. It's probably the most common unit, especially if you're looking at like certain power tools. They measure how fast it spins in this unit. Yep. RPM. So revolutions per minute. So when you're dealing with angular velocity or angular speed, those are the 3 units. But I always want you to use radians, unless the directions say otherwise. Okay. All right. So let's look at this diagram. And what I've done is I've drawn 3 different colored circles on a disk. And what's the formula for distance? That relates distance, time, and rate. Anybody remember what the formula is? Yeah.
Is it speed times time?
Distance equals, yeah, speed times time. Distance equals rate times time. So what I want to do now is I want to take this object and I want to spin it 1 time and just watch what happens. We'll go around 1 time. Okay. Anybody describe to me what just happened there? Yeah.
The green one had to travel further than the black or the red one.
Yeah, the green one traveled farther than the black or the red one. It definitely had to travel farther because it was further out from the center. And if you trace the path that it moves, it's making a bigger circle than the red and the black one. But how about if you compare the time? Like the time it took for the red one, the black one, and the green one to all go around 1 time. All the times are equal. So what does that mean? If the green one is covering more distance in an equal amount of time? Yeah?
It's going faster.
Right, I mean the green one is going faster. So then how do you describe the speed of this spinning? Because every single dot here is moving at a different speed. Like would you say the black dot doesn't move at all? That just stays right in the middle. So would you say the speed is 0? Because the black dot doesn't move? Or would you describe the speed using the green dot, or maybe a dot on the edge, which would be going even a little bit faster than the green one? It starts to get confusing. So when something is spinning, we don't try to describe the speed of it using a formula where we think about it linearly, because it's not moving in a straight line. When we want to describe the speed of something spinning, we describe it angularly. That way I could say all of these dots are making 1 revolution in, maybe it took 3 seconds. That's the speed. 1 revolution per 3 seconds. What we don't care about with angular speed is the size of the revolution. That's not important. Okay, so we're making 1 revolution in 3 seconds. So angular speed, we're always going to use radians per, and then the time unit, I don't care what you use. I would just use whatever's in the problem. Minutes, seconds, just whatever they give you. Now, if you compare that to linear speed uses units like feet, miles, inches, centimeters, anything that would measure something that's moving straight, not rotating. And common time units for linear speed, hours is pretty common, like miles per hour, kilometers per hour. Seconds is also common, like feet per second. Sometimes they measure like if you do archery or different things, they measure how fast the arrow is moving in feet per second. Any question on the difference between angular and linear speed? So now we're just going to practice a few conversions. In order to convert between different units, we're not going to use anything really fancy for formulas. We're going to use what's called dimensional analysis, and we'll cancel out the units that we don't need. There are certain conversions you need to know. So conversions you need to know would be how many seconds in a minute, minutes in an hour, hours in a day, days in a year. Those would be the time conversions. Distance conversions, you need to know how many inches in a foot, how many feet in a yard, how many feet in a mile. That's pretty much it. And then angular conversions, you need to know how many degrees in a revolution and how many radians in a revolution. Okay, if it's any other conversion besides the ones I just said, I would give it to you. So you wouldn't have to know like how many millimeters in an inch. It's kind of a weird number to memorize. It's 25.4 roughly, but you don't have to know that. Yeah.
Well, how many radians are there in a revolution?
How many radians in a revolution?
Or whatever you said.
Yeah.
2. Is it 2 pi?
2 pi. Yeah. 2 pi radians in 1 revolution. Yep. All right. So I'm just going to start off with a very straightforward one that's just converting time units. One time unit to another time unit. So let's think of 3 days as a fraction. Let's put it over 1. So we're going to multiply by a fraction. In that fraction, I want to cancel out days, and I want to eventually get to minutes. But there's a unit I have to go through in between. What's the unit that's going to get me from days to minutes? Kind of bridges the gap. Yep. Hours. So let's start by changing days to hours. Where would days have to go?
The bottom.
Yeah, because I'm trying to cancel it out. That's the idea of dimensional analysis. We're going to cancel out days. You can put hours in the top. And now you need to tell me a true statement that relates days and hours. Give me any true statement you want, preferably something simple. Yeah?
1 day is 24 hours.
1 day is 24 hours. Yep. Days in the bottom, days in the top. Now you're left with hours. Okay, let's do it again. This time we want to get from hours down to minutes. So we want hours to cancel. Where would hours go in the next fraction? Go in the bottom. What unit is going to go in the top? Minutes. And now I need a connection between minutes and hours. Yep.
60 minutes in 1 hour.
60 minutes in 1 hour. Hours in the bottom, hours in the top.
It's chemistry all over again.
And now we just multiply straight across. Sometimes the denominator comes out to 1. It did in this case. If it doesn't, then we have to use it. But this time you don't need it. So 3 times 24 times 60. Okay, it's 4,320. And what's my label? Minutes. Because that's the label that's left right there, minutes. Okay, so that was just converting a time to a time, a bigger unit to a smaller unit. Now we're going to try a speed. Okay, the difference with a speed is a speed has 2 units. It has a distance part to the unit, and it has a time part. So in this case, we've got to fix both. So we have an object that's traveling 50 feet in 1 second. 50 feet in 1 second. Okay. It doesn't matter which one you fix first. Maybe let's deal with the seconds and let's get that to hours. What unit is going to help get me from seconds to hours? Minutes. And where would minutes go? Top or bottom? Bottom. Seconds would go in the top. And what's the connection between seconds and minutes?
60 seconds to 1 minute.
60 to 1. And if you stop there, you now have a speed in feet per minute. Okay, we got to go one more step with the time unit. We got to get minutes to hours. What would you multiply by for a conversion here to change minutes to hours?
60.
Yeah, give me the whole fraction. Yeah.
60 minutes over 1 hour.
There are 60 minutes in 1 hour. Now, if you stop there, you have a speed in feet per hour. They want miles per hour. So we're close, but we got to fix feet. Okay. Now we want feet to disappear. Where's feet going to go in the last fraction? Bottom. And what unit's going to go in the top? Miles. Even if you don't know how many feet in a mile, you should be able to get to that point, because now your units are correct. But now we need the numbers. How many feet in a mile?
Yeah.
5,280. Yep. So this time when you multiply, you do not have a 1 in the denominator. So we're going to divide by 5280 at the very end. So we got 50 times 60 times 60. That's the numerator. 50, 60, 60. And then divide by just 5,280. So it's 34.09 miles per hour. Now, you do sometimes see that with a 3-letter abbreviation, MPH. I'm going to stick with writing it like a fraction because I don't want there to be confusion. Like if I write RPMs, that's traditionally revolutions per minute, but maybe you would think radians per minute. So I'm not going to use 3-letter abbreviations for the speed. Okay. Any question on that one? What kind of speed is that? 50 feet per second. Yeah? That's linear. It's measuring the speed of an object moving in a straight line. And you converted from linear to linear. So you just went linear to linear. Okay, that's what we did in that problem. Let's look at this one. 200 radians per second. And they want us to convert to revolutions per minute. What kind of speed is 200 radians per second? Yeah.
Angular speed.
That's angular. We're measuring the speed at which something is revolving, spinning. So we're going from angular to angular. Angular to angular. So we just did linear, linear, now we're doing angular to angular. So we're traveling 200 radians in 1 second. All right, so you tell me, what, I'm gonna need a couple fractions, actually just two. But can anybody tell me what the first one would be? Yeah.
60 seconds over 1 minute.
60 seconds over 1 minute. Okay, now you got radians per minute, you want revolutions per minute. Can someone give me where my units are gonna go? Just the units, no numbers in the last fraction. Yep.
Revolutions over radians.
It's gonna be revolutions over radians. Now we've got the right units, revolutions per minute, but I need the connection. What am I going to fill in for how many radians in a revolution? Yeah. 2 pi. It's 2 pi radians in 1 revolution. And again, it's not something I would tell you on the test. It's like I wouldn't tell you it was 360 degrees in a revolution either. You each have to know that. Okay, so now we're going to multiply straight across. Be careful though, you do need parentheses in this one. 200 times 60. You don't need it in the top. Where you do need it is the bottom, when you divide by 2 pi. That's the correct answer. If you don't put parentheses, you're going to get this. That's definitely not the same answer. What's the difference? What did it do in the bottom one? Yeah?
Did it divide the two and then multiply the pi after?
Right. It took 12,000 divided by 2 and got 6,000. And then it did 6,000 times 3.14. And that's how it got 18,000 something. That's not right. You wanted 12,000 divided by 2 pi. You wanted the 2 in the bottom with the pi. So 1909.86. Okay, so that's spinning pretty fast. I mean, almost a couple thousand revolutions per minute. It's pretty fast. I mean, I guess if you compare it to some power tools, like my Dremel goes at a minimum of 5,000 revolutions per minute up to 40,000. So, but
You know that off the top of your head.
I know that. Yeah, it's good. I just know it because it's a variable speed, and I used it recently, so I was looking at it.
What's the? I don't know. I was just wondering the fastest a car engine's ever spun.
Well, regular cars probably don't want to be above like 6,000, 7,000 for a long period of time.
I've got mine to 8,000 before.
Yeah,
Just by going normal speed because the transmission's bad, it just does that.
yeah, that's probably probably not great. Yeah.
That's the least of my concerns right now, though.
So let's look at our last question. Okay, so last question. It says we have a wheel, and they're telling us the size of the wheel, and that's going to be important. It's rotating at 1850 RPMs. Part A, I'm going to skip Part A. I'm going to rename Part B Part A. Because Part A, originally, was doing what we just did in this problem, but reverse. Instead of going from radians per second to revs per minute, it was revs per minute to radians per second. It's kind of the same. What kind of speed is revolutions per minute? That's what RPM stands for. What kind of speed is revolutions per minute? Caleb? That's angular. What kind of speed is feet per second? So we're making a jump here from angular to linear. It's the first time we've done that. So the way you could imagine what's happening is, let's say you had a tire on a machine. It had a radius of 18 inches, and it was spinning at 1,850 RPMs. If that tire fell off the machine and it landed upright and didn't lose any traction, but it just landed right on the ground and then just started rolling, we're basically finding out how fast it would be rolling on the ground, like coming at you. That's the idea of what we're doing.
Scary.
Okay. Same idea, like if you had a rope, when you had like a weight on the end of it and you were swinging it and you let it go. Like if you were swinging it at like 10, that'd be fast, maybe like 5 revolutions per second, you could probably do that. And then you let it go, all of a sudden it's going to take off in a straight line. So your angular speed is being converted into linear. Right? That's what we're figuring out. Okay. So anytime that we want to convert from angular to linear, we want to be in revolutions. Time unit doesn't matter. Okay. I mean, eventually we got to get seconds, but revolutions is what you want to be in. Okay. So 1850 revolutions per minute. Let's fix the time unit, because that's a quick one. What are we going to multiply by to fix the time unit? Yeah.
60.
1 minute over 60.
Yeah, 1 minute over 60 seconds.
I knew what you were thinking.
1 minute over 60 seconds. Okay, so now you've got revolutions per second, but they want feet per second. Now, feet is ultimately what they want, but what did they give me for a length unit in this problem?
18 inches.
They gave me 18 inches, so I can go to inches first because they gave me inches, and then I can go inches to feet. Right, so let's start with that. We're going to try to get rid of revolutions now, and we're going to change to inches. So where would revolutions go in the fraction? Bottom?
Denominator.
Denominator? You sure?
What did you say? You said revolution.
I said where would revolutions go? Yes.
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 I'm sure.
Okay. So revolutions goes in the bottom, and then what length unit is going to go in the top? Inches. I know, eventually we want feet, but inches is okay for now. So revolutions is gone, and now your units say inches per second. How many inches in a revolution? Yep. 18 inches in a revolution? Every revolution?
Yes.
So like, let's pretend the Earth was circular orbit around the sun, completely circular. That's 18 inches too? A little further.
Yeah.
Why is this conversion a little bit different than some of the other conversions we've done so far? Yep.
Because it goes from time to distance.
Because well, we're going from angular to linear, so we're still going from speed to speed.
Okay.
But we're going from angular to linear, but what's different about the number of inches in a revolution versus me asking you how many seconds in a minute? Yeah?
It changes based on the shape.
Yeah, this changes. How many inches in a revolution? How big of a revolution are you making? Is it like this? Is it like this?
So that's why they gave us the 18 inches.
So we need to know how big of a revolution we're making. One revolution is also known as the what? Yep, the circumference. So like imagine you had a tire like on the ground, and you mark that spot, and then you roll the tire one time until that spot is back on the ground again. If you measure how far the tire rolled to get over here, that's going to tell you the circumference. So we're converting something that's going in a circle measurement into something that's now being a straight line measurement. So how do you figure out the circumference of a circle? Julia? Yeah, circumference is 2 pi r. And what did they say our radius was in this problem? Dylan? What's our radius in this problem? Yeah, 18 inches. So we're going to find the distance around the circle. 2 pi times 18, that is 36 pi inches. That's the circumference of this tire. So it's 36 pi inches to go all the way around one time. So 36 pi inches in one revolution. And that's a conversion you have to figure out every time with the circumference formula. Now there is one more step. They don't really want inches, they want feet. So what are we going to do to change this over to feet? Yeah. Multiply, yep, can you give me my whole fraction? So we get the units and everything right? Nico? 1 foot over 12 inches. Now inches cancels. And if you go straight across, you have a speed in feet per second. So let's see how fast it's going. So we got 1850 times 36 pi. That's it for the top. And we're going to divide that by, we should put parentheses, 60 times 12, because we're dividing by two things multiplied together. So that's a speed of 290.6 feet per second. Roughly. Okay, we don't really think in feet per second. We think more in like miles per hour. So 290 feet per second. It's almost 300 feet per second. When we did this problem, 50 feet per second was 34 miles per hour. 300 feet per second is how many times faster than 50? It's about 6 times faster. So if you go 6 times faster than 34, that's a little over 200. So that tire came off the machine and was rolling at 200 miles an hour. Probably not going to get out of the way. Think about 290 feet per second. That's like a football field every second. So if you had like 3 or 4 football fields between you and the tire, yeah, you'd have 3 or 4 seconds to move.
Oh my god.
But 1 football field?
Good account for friction.
Maybe not.
Yeah, it didn't account for friction, true.
Yeah, it would slow down a little bit.
So maybe,
For
maybe
my
I had
awesome
3.5
reflexes.
seconds. I have an extra half a second.
All right, so we're going to take a look at just the page 324. So 56 to 59, and 70 and 71.
Okay. That's scary.
Yeah.
And then tomorrow will be 335.
Anything that short is not.
Yeah, no. You're guaranteed to cry. At least once.